So we're going to be going over water supply right now. So we're going to be using this packet that you picked up. It has to do with water supply, wastewater, and stormwater runoff analysis. When you look at this packet, when you first open up, you'll see a couple pages of general formulas, some of which we'll be using right now. And then after the first couple formulas, it goes over residential water supply. All right, in this presentation, the first 2 pages are kind of the notes are given to you. And then as you see, the next 2 pages, we'll be writing out some notes here. All right, so with that being said, I'll switch back over to this when we get to the part where we're actually gonna write out the notes. Otherwise, I'll be using this presentation. So for residential water supply, things that we're going to be going over are ideas of why we treat water, what we use water for, what the general parts of a water supply system are, sources of water, how we treat water, how we store water, then the distribution system, definitions, and most of the time we're going to be talking about calculating water supply pressures because that's where the analysis comes in. So why we treat water. A long time ago, we realized that we need water for survival. Almost all structures, if it's residential, commercial, industrial, they all need water. And they all need water. Some of the important things that they need are proper flow rate, pressure, and quality to be able to be useful. So some of the general uses that we primarily use water for are bathing, toilets, cleaning, food preparation, cooling, fire protection, industrial purposes. But like the really big important one here is the one at the bottom, drinking water. Drinking water is by far the most important use of water in our society. So here you see a general layout for a water supply system. You have a water supply. So this one's showing a superficial, like a lake or something like that. It doesn't always have to be on the surface. It can be underground. Either way, there's a supply of water from somewhere. All water, no matter what, has to be treated to some level. So whether it's just like a very basic chlorination or something like a disinfection, to much more complex chemical treatments to remove other harmful substances from the water. There's always some kind of treatment to make sure that it is drinkable. Once you treat it, you have to store it somehow. So a lot of times you see large water towers all over the place. You see one right next to Main East, the one at Advocate Lutheran General Hospital. And then there's a bunch of them around. So then from the storage, it doesn't always have to be in those big towers. It can be, there are man-made reservoirs that are used for this too in some places. And from those locations, it gets piped through a piping system out to the consumer, which is, again, either residential, commercial, or industrial. The two different sources that we have for water, we have underground aquifers. This is, a lot for drinking just because the water, it's so intensive to bring it up from the under the ground. So you only want to use it for like limited purposes. And also the water is usually so clean when it comes from the ground that it requires very little treatment, which is, usually a really good thing. Also industrial facilities, oftentimes, if it's an industrial facility that requires a lot of water, it will be purposely located next to a body of water where it's much easier to get access to water. You'll see that, here in Chicago. One of the big reasons that Chicago is where it is because of the Chicago River and Lake Michigan and all that. You see New York and San Francisco; those are right next to large bodies of water. A lot of manufacturing facilities, they're going to be located next to some kind of body of water if they need to. And then let's see. So how that works, you have an aquifer underwater, it gets sucked into a pump and then pumped up to the surface, and then the whole process, the treatment process starts. Other sources of water, you have, lakes, reservoirs, rivers. A river can be dammed to, like you see down here, to create a big lake. And then reservoirs can help store water, also control water as it flows through a river to prevent flooding. Water treatment depends on what the quality of the water going into the system is. As I said, it can be very quick and easy, where it could be just a little bit of chlorination, disinfection, basically. Chlorine is one of the primary chemicals we use for that. Here in Chicago, besides chlorination, the only thing that you usually really have to do is a little bit of filtering just to remove like large particulate matter outside of the chlorination, and they usually add a little bit of fluoride for dental purposes. But the water we get out of Lake Michigan is really pretty clean. Other places they have to do a lot more. Some of the other Great Lakes where they have algae blooms and stuff like that, there's a lot more treatment that needs to go into those things. You can have like desalination plants, which again is a huge thing on the coastal areas. So it just depends on what the quality of the water is, or what the situation is with the water coming into the system. All right, once you've treated the water, then you need to store the water, and that's where you see these big towers around here. And this is a big number here. 1 psi of water equals 2.31 feet of water. So we're going to talk about where that comes from, or how that works. So we're going to actually kind of switch over here temporarily to kind of understand what that means. So it said that 1 psi equals 2.31 feet of water. All right, so the concept is, if you have like a really tall cylinder, imagine like a big beaker from your science class, and you started filling it with water. All right, so you start putting water in here, water, and then you get to the point where that water fills up 2.31 feet. All right, and then in that you take 1 square inch column. So it's a rectangular shape where it's a square at the top edge and the bottom edge. All right, that column of water will weigh exactly 1 pound. And so that is 1 square inch here. And so the pressure pushing on that 1 square inch is 1 pound per 1 square inch, or 1 psi. All right. So when we're talking about water pressure, a lot of times, this is a very old method of analyzing water systems. It's a very old thing to do, and so a lot of times we're going to talk about pressure as something you're going to see very soon here. A head, they talk about the head, which really will relate to pressure. But head is measured in feet, whereas pressure is measured in pounds per square inch. So we're going to need to be able to convert between the two. All right. So, and that's going to kind of tell us how to do that. All right. So, water distribution systems, there are 2 general types. Of the older system is the branch system here, and then the more modern system is a loop system. The older system, the branch system, it's easier to build. You usually have 1 main line, and then you have little branches coming off of there. The problem with this is if you have a break, say like this part right here breaks, all of these branches, all of these houses here will lose water until you fix that. All right, so a single break can cause a lot of places to lose water supply. Whereas a loop system, say if you lose, if this part right here breaks, instead of this whole area over here losing water, the water can go around this way. And so using different kind of isolation valves and water flowing in more than one direction, you can get water to lots of places and minimize disruption. All right, so those are the 2 general types of systems, a branch and a loop system. You can kind of see that you can sort of turn a branch system into a loop system if you kind of make a few more connections. And that's a lot of times what we're kind of working to do nowadays, is to update older systems to make them more redundant and more able to handle issues like that. All right, when you create a water distribution system, you use pipes. Nowadays, the material that's used is used kind of thermoplastic or ductile iron. Sometimes if it's a really large system in the major cities, you'd see a reinforced concrete for very large mains. Older systems that are trying to be replaced are cast iron and asbestos cement. Cast iron because there's a lot of rust and it can, cause, it's actually, not so detrimental to health, but it's more issues around, corrosion inside the pipe, and you get rust that causes lots of clogs. And then asbestos cement, obviously the asbestos you don't like. Typical distribution pressures. You'd like to see the pressure coming out of your pipes, out of your faucets at between 65 and 75 PSI. You'll see that there's the minimums and the maximums are a little bit different, but that's the ideal pressure. Something you definitely don't want to go over is 150 PSI, unless it's an industrial purpose that requires more. All right. So the minimum that if you're designing or building a water system, the minimum pressure you'd ever want coming out of a pipe at a home as a residential place is 40 PSI, and the maximum is 80 PSI. The reason for this, 40, if you're taking a shower, if you're trying to take a shower, do something, fill up a bucket of water. If it's less than 40 PSI, it's just not going to be enough pressure. You're not going to be, able to really get yourself clean, or it's not going to be able to fill up that bucket very quickly. Maximum pressure is 80 PSI. If you go over 80 on a regular basis, your pipes, your fittings, your valves are all going to have issues. They're going to break often. For commercial, and if the system does have too much pressure, you can use something called a pressure reducing valve to help you in that situation. Commercial industrial facilities might require heavier or higher pressures, but again, the fittings and the pipes that are used in those settings are much more expensive and able to withstand those kinds of pressures. All right, so now we're getting into definitions. So this is where we're going to switch over to our notes so we can kind of do a dual screen here. All right, so head. So the head, like I said before, it's kind of a measure of energy. In the fluid, and here we're talking about water. And the way we measure it is height equivalent, meaning feet of water. All right, so again, the concept is imagine you're in a pool and you dive down 2 feet. The amount of pressure on your eardrums is the equivalent of 2 feet of head, right? There's 2 feet of water standing on top of or above your ear. And so if you converted that into a pressure in PSI, you could do that. Oftentimes this is referred to as a head. All right. So static head is when the water is not moving. So kind of like in your physics classes when you did potential energy for something that was at rest, and kinetic energy when something was moving. Static head is kind of like your potential energy. Of water at rest, meaning not moving. All right. And so that's when you've stored your water in these big, large towers. If it's just sitting there, the water is static, it's not moving, and you have a static head, a static pressure at the bottom of this tower of how much water is sitting above it. All right. Again, it's measured in feet. And the static head is equal to source elevation minus discharge elevation. All right, so the easiest way to explain that is, so for example, we have one of these water towers right here, and the pipe comes down, and say there's a little spigot right here. All right, so this is all full of water. And so that is the amount of, that's the height. So this is the source elevation. This is the discharge elevation. And so that is the static head. All right, so in our example here, let's see if it'll load. So in our example here, say that this elevation up here is 943 feet. The elevation at the bottom is 890 feet. And so the static head there, so again, I'm saying this was 943, this was 890. The static head is equal to 943 minus 890 is equal to 53 feet. All right, so it's simply just a difference in height. All right. But as soon as the water starts moving away from this tower, you have head loss. So, before we talk about that, we can talk about static pressure. And static pressure is where you take the elevation of 53 feet of static head and you convert it to a pressure. So again, imagine you're 53 feet underwater. There's a pressure on your eardrums, right? And so the way you do that is you divide 53 by 2.31. That's the conversion from PSI to feet, and you get 22.9 PSI. So if you happen to be 53 feet underwater, you would have 22.9 pounds of pressure pushing on every square inch of your body. And that's why your eardrums would very likely have a difficult time withstanding that kind of a pressure. All right. So there's a way to directly convert from head to pressure. All right. So going back here for a second, if this was the scenario, if you had, if your house had a water tower next to it and you had 53 feet ahead, that water tower was only 53 feet tall, you would notice that you'd only get 22.9 PSI of water pressure coming out of that pipe. Would that be enough to to provide you enough water pressure? Well, no, it wouldn't, because a house needs at least 40 PSI, and this would only give you 22.9 PSI. So this water tower would not be tall enough for a residential situation. The way you would kind of back calculate is if you need a minimum of 40 PSI, and every 2.31 feet gives you 1 PSI, so you did the multiplication, you would find that at a minimum, a water tower needs to be 92.3 feet tall. All right. And so if your house happened to be like literally right here next to the water tower, you could, the water tower would need to be 92.3 feet tall. But for most of us, we don't live directly right next to a water tower. We live, up to, miles away. And so as water travels through the pipes from this water tower to your house, you actually lose pressure in the pipes. And so that gets us to our next section of notes, head loss. All right, so head loss is energy loss due to friction. So you lose it in the pipes, you lose it in the fittings, which are like elbows when you change direction, T's again when you change direction, valves when you try to control the flow, etc. Other things you can do is equipment, so like pumps and things like that. So major losses. The major losses, the where you lose the most, is friction in the pipes. So as the water moves through the pipes, it rubs up against the sidewalls of the pipes, and therefore it loses a lot of energy, a lot of head. All right, minor losses. Those are your fittings your bends, and your valves. All right. The way in which we calculate head loss is this equation. It's going to be a really crazy looking equation, but it's the Hazen-Williams formula. All right. And when you see it, it might look a little strange to you. So it's this formula here. So HF is equal to 10.44 times L times Q to the power of 1.85 all over C to the power of 1.85 times lowercase d to the power of 4.8655. All right, what all these things are. So H sub F, that's your head loss, meaning the amount of energy you're losing. Capital L, that's your length of pipe measured in feet. Q is your flow rate, so how much water in gallons per minute, GPM. C is your Hazen-Williams constant. So this all depends on the type of material your pipes are made out of. And then lowercase d, that's your pipe diameter, measured in inches. So, very brief backstory. There's two guys, two researchers, one named Hazen, one named Williams, and they did a whole bunch of experiments to just kind of figure out how much energy you lost in your pipes when you're sending it from one place to another. All right. But the thing is, when you use this formula, so we'll talk about that in just a second. So again, as I said, your Hazen-Williams, your C values, they all depend on the different types of materials. So different materials have different C values. You have typical ranges. You have clean new pipe, which would be ideal, but doesn't really work all the time. So what we use are these numbers. All right. Whenever I'll tell you, we do a problem, I'll tell you the type of material, and you just use this number here for your C value. All right. So when we use Hazen-Williams, it assumes that it is a straight line from the source to the discharge or wherever the water is being run to. So if you went to a water tower and then drew a straight line from that water tower to your house, this formula assumes that's the path water travels. But we know that water doesn't travel in straight lines. Water travels in all kinds of twisty, turny ways. Usually the water lines follow the roadways, so you can follow probably a grid pattern of how the water actually gets to your house. So what we need to do is we need to calculate this whole thing as if the water were in a straight line. All right. So the way we do that is you turn these minor losses. Those are all your fittings and everything. These are fittings, etc. And we use the Hazen-Williams charts to turn them into straight pipe. So the idea is every fitting has an equivalent length of straight pipe. So if you have like a 90-degree elbow, that's the same as, say 1 foot of pipe. I'm just making that up. I think in actuality, like a 90-degree elbow would be something like 10 feet of pipe. All right. And so the whole point is you need an equivalent straight pipe length. All right. And that's, again, when you look at the front of your packet, you're going to see on this very last page here, that's where it is. It's the equivalent lengths of generic fittings. So like for an elbow, if you have a 1/2 inch pipe, an elbow for a 90-degree thing is worth 3.6 feet. All right. If you have, something larger like a 10-inch pipe, an elbow could be worth, could be the equivalent to 14 feet of pipe. All right. So that's how that works. All right. And so the whole concept also is that Hazen Williams measures as the water is flowing through the pipes. So before, when we just talked about the amount of head in the pipe, it was all static head, right? Remember, the water was just sitting at the top here and sitting, all through this pipe down to here. So nothing was moving. It was very static. All right. So now things are going to be moving from here out to here and out. And so when things start to move, that's when things become dynamic or moving. All right. And so now the concept is that when we're using dynamic head, this is head for moving water. All right. It's still measured in feet. And very simply, it is the dynamic head is equal to the static head, which again is water not moving, minus head loss. All right, so however much head you started with, the static head, minus the amount of friction that, or energy you lost due to the friction in the pipes. Okay? All right, so that's your, there's a whole bunch of examples here of calculating head loss. I'm not going to go over that in this presentation because we're going to do these examples. So again, big picture is dynamic head is the amount of, it's the head you started with, static head minus the head loss. All right. And then the last thing is the actual pressure. So when you're actually at your tap and you want to verify that you have enough pressure, you take your dynamic head, say DH, and you divide by 2.31. Remember, that was your feet per PSI, right? If you did the calculation, this is in feet divided by feet per PSI, you end up with PSI. All right, so that's the basics of how you do water supply. And after this, we're going to go over some examples.